Hello, welcome to today's video, and we're going to be looking today at Unit 27 on the BTEC Static Mechanical Principles in practice, and we are looking at calculating all of the forces within a truss. This is geared towards the assignment task for outcome A, where you need to calculate the forces within a truss containing 12 members. So we'll have a look at the truss in a moment. Well, there are two main methods for calculating forces in a truss: the method of joints and the method of sections. We're going to the method of joints in this video. It will probably end up being a long video. I will try to put various sections into chapters for you on YouTube so that it's easy to find where we're at. But we'll make a start and we'll carry on here as we go. So if we look, we have a truss. And this is a truss with an external force acting upon it. You can see the external force here. And it is made up of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 members held together by 8 joints. Okay, the joints are in our analysis are always theoretically dimensionless pin joints, i.e. they won't affect any calculation, will only work in forces. And our truss will always be fastened at one end by a pin joint here and on a roller bearing here. Okay, I've tried to simplify this somewhat by having the vertical and the horizontal members both measure 2 meters and an external force of 10 kilonewtons on there. For the purposes of all our calculations in this example, then all of the angled members will be at 45 degrees. However, it's important when you're using this as a guide to remember that when you're working on your own truss, the dimension will be set by your own question. Okay, so just be clear, where I put 45 degrees in, yours might be different. Okay, so because we have a pin joint here, this part of the truss can't move horizontally or vertically. Therefore, there are two reaction forces, one in the horizontal direction, R1x, and one in the vertical direction, R1y. However, at this end of the truss, it's a roller bearing. It can move horizontally, but it's being supported vertically. Therefore, there's only one reaction force at that end, which is R2 in the y direction. These reaction forces are the first thing we have to calculate. Okay, these three reaction forces are the first things we have to calculate before we can go into any more detailed truss analysis. And so we're going to move on and we're going to look at how we do this. The simplest way is to now take the whole truss as one solid object. Okay, so I've kept the vague shape of it. That's what we tend to do when we do this. Put the dimensions on. So there are 4 beams horizontally between this end and this end. So 4 times 2 meters is 8 meters. And there are 3 beams from this end to where the 10 kilonewton force is acting. Okay, so that is 6 meters from this end. So now we've got our measures. What we're going to do is look at our 3 equations of equilibrium. Statics is all about things not moving. And so if we look, put our reaction forces in, we're now going to equate these forces and we're going to see how we go. So when equating forces, we need a convention for our signs. I tend to always take my sign convention as being up is positive and right is positive. That ties in with how we draw a graph in England especially. That top right quadrant of a graph is our positive quadrant. Okay. The other thing I also do, which I've not drawn on here, but is a convention I use, is that anti-clockwise moments are positive. That comes from my background in robotics. So, if we look, there are 3 formulae that we need to remember when we're calculating statics. The sum of all horizontal forces, sigma fx, is equal to 0. the sum of all vertical forces, sum of Fy, is equal to 0, and you'll see one of my things just got kind of there. If we look at our horizontal forces, we'll just sort this out now. We have one horizontal force here, R1x, and no other horizontal forces. If this external force were acting at an angle, it may create a horizontal force, meaning we get a horizontal reaction force. But in this example, R1x is pushing to the right, and there are no other forces pushing to the left, so R1 of x is equal to 0. And you should, if you're doing the BTEC level 3, you should expect this to be the case. It's a very, very harsh centre would ever give you something where you have R1 of x equal anything but 0. Back to where I was. The sum of forces in the y direction is also equal to 0. So up is positive, I've set that down here. So that means R1 of y and R2 of y equals a 10 kilonewton force pressing down. So R1y plus R2y minus 10k is equal to 0, and simplifies to R1 plus R2 of y is equal to 10k. Now there's there's nothing else we can do with that at present, because we don't know what R1 of y is and we don't know what R2y is. So we come to our third equation. The sum of all moments is equal to 0. So we need to take moments about a fixed point of this body, this truss. My principle is always to take it around point 1, R1, where R1 is sitting. Okay, so what we've got is that R2 of y multiplied by 8 meters from our pivot point minus 10k of y, because it's trying to turn it. So R2 is turning it anti-clockwise, so it's positive. 10k is turning it clockwise, so it's negative. And we've got R2 of y times 8 meters minus 10k multiplied by 6 meters is equal to 0, because all of our force equals 0. Okay, happy with that so far. What we'll see now is we'll take these two forces, okay, and we're going to take this bottom equation here. 8 times R2 of y is equal to 60k. Hopefully that's a simple rearrangement for you guys, that R2 of y is 60k divided by 8, which is 7,500 newtons, or 7.5 kilonewtons. Okay. If we then take that 7.5 kilonewtons, put it back into the first equation, we see that R1y plus R2y is 10k, R1y plus 7,500 is 10k, which means R1y is 10k minus 7.5k, which gives us 2.5 kilonewtons. Okay. And that gives us our reaction forces for this truss. So we can draw the truss with its reaction forces sitting there. Those reaction forces are calculated exactly the same way as you would for a simply supported beam. Now we've got 8 different joints to analyse, 13 beams, which means there's going to be 8 different sets of 2 equations for each beam. For each joint, sorry, not beam. Okay, so what we're going to do to simplify is to label our joints. Now, personally, I tend to start at one point and go clockwise. Free to label them how you want. But I start in the bottom left with A, and then just labelled them all the way around to H in a clockwise motion. Okay, that is done. So now we know what the joints are called. We're going to add the forces. Now to do this, I've just slightly redrawn the truss a little bigger. Basically this diagram was one that I drew a few years ago and didn't allow an awful lot of modification. This version of it is a bit more user friendly, shall we say. So here's my truss, exactly the same design, just slightly bigger, easy for us to see. We're going to take the beams out of the diagram and we're going to replace them with tensile forces. Okay, so we're going to assume that every force is tensile. Okay, now when we look at that, what we take is the force between point A and point B. We're going to remove that beam and we're going to add an inward pointing force we've called AB. So a tensile force on that beam is creating an internal pull at joint A. Okay, and we just go around again and we do exactly the same thing. So we replace BC, CD, DE, EF, FG, and so on, all the way around until we have a still very complicated looking free body diagram. And it's at this point you have all freedom. Okay, we're going to pick a joint, ignore absolutely everything else within that truss, okay, and use that point to determine the forces acting on that point. Okay. But there is one rule. We have two equations per joint, the forces acting horizontally and the forces acting vertically. So if we have more than two unknowns, we would need more than two equations. So we can only use the method of joints where we know all but two of the forces acting on their own. For instance, if we look here, point B has got AB, BH, BC and BG all acting upon it, and we don't currently know what any of them are, so we can't start at point B. If we look at point E, point E, we have a 7.5 kilonewton reaction force, we have force DE, and we have force EF. There's two unknown forces, so we could use point E. However, I'm very OCD and I look at point A, and point A is in the same situation, 2.5 kilonewton reaction force, force AB and force AH. Okay. When we're doing our calculations, we're going to use the same conventions all the time. Okay, and I'll bring that up in a minute. Alright. If our forces become negative, then the easiest way is to use the name of the force, rearrange the equation, and then put the forces in, because then we don't lose minus signs. It will make sense in a moment as we go through this. Okay, so we're going to pick point A first. So I'm going to get rid of everything else, bring my free body diagram, and this is all we would sketch. Point A is an individual point force. Okay. Add in our sign convention, which will be there in a moment. There it is. Okay. And now we're going to equate horizontal forces. We're going to equate vertical forces. So, sum of forces in the x direction is equal to 0. And I would say this is how I tend to do it on a page as well, is you'll see I'll have split my page down the middle, done x, and I'll do y in kind of, sorry, I can't get my cursor to work. I'll do y in this part of the screen here. Okay, you'll see it in a moment. So if we look at this, sum of forces in the x direction, we have got force AH, which is horizontal and pointing to the right. Here. AH. We also have the horizontal component of force AB, which is acting at 45 degrees to the horizontal. Okay. If we remember our rules of right angled triangles, then the horizontal component of a force is the hypotenuse multiplied the cosine of the angle. The vertical component of the force is the hypotenuse multiplied by the sine of the angle. Those are two rules that are very important to remember for this analysis. They'll come up all the time. Okay, so we've got that. Again, we can't do anything here because we don't know what AB is, we don't know what AH is. We've got two unknowns, we've got one equation. Okay. However, if we look at the vertical forces, some of the forces in the y direction, then 2.5 kilonewtons is pointing upwards here, plus the vertical component of AB, which is also pointing upwards, so it's positive, which is AB times the sine of 45 is equal to 0. Now we've got one unknown in this equation, so we keep working, we rearrange this, we get that AB times sine 45 is minus 2,500, and AB is minus 2,500 over sine 45, which gives us our first force. Force AB is minus 3.54 kilonewtons. Minus because this is not a tensile force, this is a compressive force. So that's what that minus sign means. But for the purposes of our calculation right now, we're just going to put minus 3.54 into our table of results. We'll worry about what's compressive and tensile at the end. Bringing it back to our forces in the x direction, we now know what AB is. AB is minus 3.54 kilonewtons. Therefore, AH is minus AB cos 45, and so AH is minus 3.54k. This is why it's important to get this sign right before we put our numbers in, because minus minus gives us plus 2.5 kilonewtons for our force AH. Going to our truss, those are those two forces calculated, so we can go back to our truss, and again this is how I would be doing it for you guys. Have the truss drawn out, okay. Get yourselves a table of results. So we've now got AB and AH. You'll note these are all the forces that I'm expecting to see within this truss, and I've worked two of them out already. And if you want, you can then rub out AB and replace that with the forces. I'm doing this purely so you can see how we build up these forces. Generally I would just leave the table at the end. It's up to you. Okay, so now we've got to work on which one are we going to do next. Well, if we look, point B, we still have three unknown forces. Point E we could do, but it doesn't really get us anywhere. However, if we do point H, then we clear this force out on part B and we're left with two. So the principle is going to do point A, we're then going to go to point H, up to point B, and we should then be able to step ourselves up, diagonally down, up, diagonally down, up, and back down. Okay, so we're going to do point H next. So let's have a look at point H. Bring those forces in. Okay. Just for us so we can see what's going on. And don't forget my sign convention. Okay. Well, I'll start not putting that sign convention on the slides in a bit. Okay. So, again, sum of forces in the x direction is equal to 0. GH is positive due to our convention down here. AH is negative due to our convention down here. This is AH, remember, our 2.5 kilonewton force. So GH is equal to AH, which means GH is also equal to 2.5 kilonewtons. Nice, quick calculation. Those bright sparks might be looking at BH thinking, I know what that is. And this is what we call a zero force member. And it's if you see two forces directly opposing each other and then a third force at 90 degrees to it, then you know that that is a zero force member. Okay. BH is upwards and positive. There are no other vertical forces in this member, at this point, sorry. No other vertical forces at this point. Therefore, BH is equal to 0 kilonewtons. What we call a zero force member. So point H is nice and quick. Done. We can come in, replace BH and GH with their forces. And again, I'm going to replace them on the diagram. We can't exactly delete that member off the diagram. Even though it's 0 kilonewtons, we can't delete it because the member is there. So we've got to acknowledge it's there, but we call it a zero force member. For instance, if BC were to break, let's say, then this would start taking some force, probably. Okay, so we've done H, we've done A, got 4 forces already. Now if we look at point B, we know what this force is, we know what this force is, and we're left with 2 unknown forces. So I'm going to do point B next. Work our way through it. Just simplify our diagram a little bit. Okay. And sum of forces in the X-ray. And again, here's where we're going to get slightly sign bogged down. Okay. BC horizontal, pointing to the right, positive, plus the horizontal component of BG, which is BG cos 45, also horizontal and pointing to the right, minus, because it's going to be pointing to the left, the horizontal component of AB, which is our minus 3.54 kilonewtons from our previous calculation. So we have to look at this, rearrange this. Yeah, there's nothing we can do because we've still got 2 unknowns. Okay, so we have to come back to our vertical forces again, Fy. You can see that minus BG sine 45, vertical component of BG, minus, because these forces are pointing down, that's why they're negative. So minus BG sine 45 minus AB sine 45 is equal to 0. That means minus BG sine 45 is equal to AB sine 45. Minus BG sine 45 is equal to minus 3.54. That's our AB sine 45. Minus BG is minus 3.54 kilonewtons, so BG is 3.54 kilonewtons. Lots of minuses in this one. Be careful. This is a tensile force. However, it is of equal and opposite magnitude to AB. Now we know BG and we know AB, we can plug our values in here, and again, watch out for this minus. Okay, that will become a plus. So BC plus 3.54 cos 45 plus 3.54 cos 45. BC plus 2.5k plus 2.5k. BC is minus 5 kilonewtons. Yeah. You will be a marvel at right angled triangles by the time we finish this truss. So we've now got what BG is. We've got BC's. You'll note I just even deleted BH. There was no force there, so I just took it off to make the diagram easier. We can do that bit on our single point force. We can't do it on the overall truss. And so we're back here. We've now got BC, and we've got BG. BG, 3.54 kilonewtons. BC, minus 5 kilonewtons. So we're basically halfway through this truss already, nearly. 1, 2, 3, 4, 5, 6, 7 more to work out. And we've worked out 1, 2, 3, 4, 5. We've worked out 6, we've got 7 more to work out. So again, we're going to look, and point C still has 3 unknown forces on it. Here. But point G, we know this force, we know this force, and we've got 2 unknown ones. Therefore, we're going to do point G next. So let's have a look at point G. Let that come in. And like I say, we're keeping the same convention, so I've not bothered keep reiterating it. Sum of forces in the x direction. So let's have a look at this. FG is positive and pointing to the right. 2.5 kilonewtons, that is GH. It's pointing to the left, so that will be negative. And we'll have the horizontal component of our 3.54 kilonewton BG force here. So we've got FC minus GH minus BG cos 45 is 0. Plug our numbers in there. 3.54 cos 45 is 2.5 kilonewtons. Fg minus 2.5k minus 2.5k is 0. So Fg is 5 kilonewtons. Sum of forces in the y direction. Vertical pointing upwards, Cg, so it's positive. Here. Vertical component of 3.54 kilonewtons, or Bg, is Bg sine 45. So Cg plus 3.54k sine 45 is 0. 3.54k sine 45 is 2.5k. You may be noticing that cos 45 and sine 45 are the same value. So Cg is minus 2.5 kilonewtons. So we've got Cg and we've got Fg from that calculation. Again, now we pop back to our truss, pop those values in the required slots, and I'm just going to replace the forces as we have done already. Okay, so now I'm going to go up, keeping this going, up to point C, where we know 2 of the forces, we don't know the other 2 of the forces. So let's focus on this one. Again, this one's slightly tricky, but it's not too horrendous. Forces in the x direction, once again. So we've got CD, horizontal, pointing to the right. We've got what's that one? BC, minus 5 kilonewtons, horizontal, pointing to the left. So and we've got the horizontal component of CF, which will be also pointing to the right. So I get CD plus CF times cos of 45 minus, because it's pointing behind us, minus 5k because it is minus 5 kilonewtons. Again, we can't do anything with that because we don't know what CF is and we don't know what CD is yet. So we need to go to our vertical forces. Both are pointing down, so we get minus CG, which is this minus 2.5 kilonewton force, minus the vertical component in CF because it's pointing downwards. We have to go to the right and then down to get to this point. So we've got minus CG minus CF sine 45. That means minus 2.5 kilonewtons is equal to CF sine 45 plus 2.5 kilonewtons over sine 45 is CF, and that is 3.54 kilonewtons. Now we have CF. We come into this bank here, put our numbers in. You'll note I've taken here, I've taken my minus and minus and made it a plus. 3.54 kilonewtons, which we've just calculated here. Rearrange that, and we get that CD is CD plus 2.5k plus 5k is 0, so CD is minus 7.5 kilonewtons. Next two forces done. So we go back and we plug those in, and you start seeing, oh, we've only got 3 forces left to get. Looking at my table, pop those forces in. DF, DE and EF. So if I go to point F, that's going to get 2 of these forces. I could do point D, but actually I'm thinking point F is probably slightly easier. There's less negative forces on it, is what I'm looking at. So we're going to look at point F, keep that trend going. Put in our real forces, focusing on point F, across again. It's just gone slightly off the screen, but you know it's a 3.54 kilonewton. So sum of forces in the x direction is 0. EF, horizontal, pointing to the right, minus FG, which is my 5 kilonewton force, pointing to the left, so it's negative, minus the horizontal component of CF, which is CF cos 45. Again, do we know all of these numbers? Yes, so we can put them in. If we don't know all the numbers, we go on to the vertical component, and that will give us one more of the forces. Looking at this, EF minus 5k minus 3.5k cos 45 is EF minus 5k minus 2.5k. EF is 7.5 kilonewtons tensile force. Vertical component, DF, vertical, pointing directly upwards, plus the vertical component of CF, which is CF sine 45, is equal to 0. So DF is minus CF sine 45, which is minus 3.54 kilonewtons times sine 45. DF is minus 2.5 kilonewtons. So we've worked our way through to those two forces. Very quick calculations at this point, because we know where we're going, we know what we're doing. Everything's right angle triangles. Those two forces drop in, and we're left just with DE. Okay, so put those forces in, and what you'll find is, and this should happen with any truss you analyse, we've now got 2 points on our truss that we haven't analysed, but we've only got one more force to find. Okay, so what we can do, well, you don't have to do this, so I'm not going to go through it on this video, because this is more making sure we pass this the level 3 assignment, making sure you can follow how to do the method of joints. We could pick, say, point E to work out what DE is, but then work out all the forces on point D and see if we get the same value, and it gives us a small little error check. Okay, but we're now going to look, and we're going to look at point E. I've picked point E purely because if we look, point E's external force is pointing upwards, and so it's going to be positive. whereas point D's external force is pointing downwards, and we've got a negative force here, a negative force here, a negative force here, and it's just more confusing, to be brutally honest. So I've picked point E. So we'll simplify that down, bring it along here a bit, and we're going to look. Horizontal forces. Minus EF, because it's horizontal pointing to the left, minus the horizontal component of DE, because it is also pointing to the left, is equal to 0 because all the forces are equal to 0. We know what EF is, so minus 7.5k plus DE cos 45 is 0. Sorry, minus DE cos 45 is 0. So DE is minus 7.5 divided by cos 45. And that is equal to minus 10.6 kilonewtons. We can check that because we can also do the sum of forces in the y direction is equal to 0. 7.5k plus DE sine 45. The vertical component of DE is equal to 0. So DE sine 45 is equal to minus 7.5k, and you'll see we've got basically the same calculation. It gives us the same answer. So we can be pretty confident that that is right. Pop to our truss, put our final force in, and we have calculated all of the forces within that truss using the method of joints system. There's one more task we need to do on the BTEC, is we need to identify which forces are compressive, which forces are tensile. While our minus signs do that because we assumed everything was tensile, for me it's always better to make it clear at the end. So what I do, and what I've done here, you can draw this yourselves. I mean, I drew it all on PowerPoint, so you can draw it all yourselves, is make my table color coded. Code the beams of my truss the same way. So red is compressive forces, black is redundant members, and blue is tensile forces. And then just go through, and you'll see there what I've done is I've taken all the minus signs out, and I've just left myself with the force and whether it is compressive or tensile, or redundant, which is the single black force on there. Okay, I hope this has been useful for you. I know it can be a long-winded job doing this analysis. There is software out there that does it for you. Once you're in the business, you're not likely to be having to do these hand calculations yourself. You know, Excel can be programmed to do it for you as well. But that is a good way through the method of joints, way of calculating all the forces in a truss. I hope you've all enjoyed that recording, and I hope it helps you all. I'll see you next time. Bye.